Hello, my name is Alexander, and today I will present to you our approach for recommending transformation rules for method deprecation. This work was financed by Arola, a consulting company in Paris, and it is also the company that sponsors my PhD. First of all, I will explain to you the problem of library update. So here you can see the scenario when a client system depends on the library. So a client system is supported by a client developer and library is maintained and developed by a library developer. So as time passes, a library releases a new version. So we call this library evolution. And when this happens, clients can either stay with the old version, but then sooner or later it will become obsolete, or they can switch and they can depend on the new version. But if they do it just like that, in many cases, clients will receive a lot of errors. Why? Because libraries are released with breaking changes, so they're not compatible with their previous versions. So what needs to be done from the client side is that when one of their dependencies releases a new version, client systems must be updated accordingly so that they can use this new version. And this is in fact the problem of library updates. So the question is, what are the changes that need to be done to the client system that dependent on certain version of the library so that it can instead depend on the newer version of the library. So if it was version n, so what are the changes to depend on version n plus k? And in fact, there are many approaches proposed to help client developers in this task, because for them it's very hard. Sometimes it can be a very hard task. So the objective of those approaches is to mine, for example, all this information, all this data, all this knowledge that we have inside the commit history and inside the source code. So to mine it and to propose it to clients in form of recommendations. So in this work, we propose to change the perspective a little bit, and instead of helping client developers, we help library developers, because we know that library developers we build our study on the assumption that library developers are motivated, they want to help their clients. So in fact, what we do, we also mine the same information from the commit history, or not exactly the same, but we also mine information from the commit history and source code, and we propose this information to library developers, thus helping them use and structure maybe the knowledge that they already have about the system, and add extra knowledge from the commit history, and like this support their clients. So we identify four ways how library developers can support their clients. So first, there is documentation, so they can write release notes or change logs, or maybe some tutorials or blog posts. Then there's deprecation. So instead of removing the functionality immediately, library developers can mark it as deprecated and only remove it in the upcoming releases. Then there is automation, so library developers can write certain update scripts or automatic rewriting rules that can be applied to client code. And there is communication, so library developers can directly communicate with their clients through forums, chats, or mailing lists. So in this work, we focus on two of those ways. So we focus on deprecation and automation. So we will mine the frequent method call replacements from the commit history, and we will generate a special kind of deprecations that have transformation rules which can be automatically applied to fix client code. Now I will explain you how this rewriting deprecation functionality works. So in this work, we focus on the Pharo programming language. So what it is, it's the pure object-oriented language that was designed in the tradition of Smalltalk, and it is also an IDE, an integrated development environment that was built entirely in itself. So why we chose Pharo? Well, in fact, the first most important reason is that we have direct access to the Pharo community. So many of the core developers of Pharo, they are members of our research group, and also we have direct connection to almost 1,000 developers that write code in Pharo. So like this, it is very easy for us. It is very convenient for us to get access to those developers and to talk to them about their projects or about their code. Second reason is that Pharo itself is very convenient for manipulating source code. So it provides very nice tools for building abstract syntax trees, for parsing source code, for parsing the commit history, for accessing different parts of code. So like this, it makes also more convenient for us to analyze the code and to communicate with the code. So here's the example of a method deprecation in Pharo. So it's you can see that the first line is just a method name, a method signature. The second line is the deprecation. It is a method call that accepts one argument, which is a string, and the string is a deprecation message. It informs clients that the method is deprecated, and in this case, it tells the client that the method was renamed to another name. So like this, the client knows what needs to be done. And finally, the method body. So the body that will be executed after the deprecation warning is fired. There's also another type of deprecations in Pharo, and this one is more interesting for us. It's the one that allows you to add transformation rules. So here you can see also there is a deprecation message as the first argument to the deprecation. It's here, the first green box. And the second green box is the second argument, which is a transformation rule. This transformation rule will be applied as the deprecation warning is signaled. First client will see the deprecation message, and then the client code will be automatically rewritten using this transformation rule. Here we can take a closer look at the transformation rule. So it consists of two parts. Both are a kind of regular expression that can match the source code. So what will happen is that as client executes the deprecated code, then the tool will automatically find which specific method called was signaled, and then this specific method called will be transformed using the consequent expression. So antecedent, it matches the method call that should be replaced, and consequent, it defines the replacement for this obsolete method call. So finally, now, okay, we have these nice transformation rules, we have this very cool technique. So why do we need still to support library developers? Well, in fact, there were studies that show that in many cases, developers, they introduce deprecations. First, developers often miss the opportunity to deprecate methods. But also developers, even when they deprecate, they often don't provide meaningful replacement messages. So they do not write any deprecation warnings or comments that contain information about what is the replacement for the obsolete functionality. So here you can see that in Java and in JavaScript, around 33% of all deprecations, they don't contain any useful deprecation messages. And in C#, it's 22%. So we did also a study in another paper on Pharo. So we analyzed, it was another research that we did. We analyzed the existing deprecations in Pharo 8, and we saw that 41% of those deprecations, they are non-rewriting, so they do not contain transformation rules, and 59% they're rewriting, so they have transformation rules. But what is more interesting is that out of those 41%, 9%, well, in fact 9% of all deprecations here, but you can see this portion, those are the missed opportunity to introduce transformation rule. Why? Because there is a straightforward way how transformation rule can be implied from this deprecation. It is just perhaps that developer who introduced the deprecations, they did not know how to use transformation rules, or maybe they did not know what is the correct replacement. So they could benefit from the tool that could help them. So here we can also take a closer look at the more structured. So these deprecations are grouped by different categories, and you can see that most deprecations that are from method renamings, and we can see that also there are many deprecations that are delete method, push down, complex replacement. But what is interesting is that also here we show the missed opportunities. So you can see that every method renaming is, if it's not transforming deprecation, then it should be, because it is really straightforward. If a method A is renamed with B, then it is a kind of rule that we can automatically apply and replay on the client code. And the same for split method, and the same for remove argument. So there is a lot of things that could be automated here. Now we will be proposing a tool for doing this in Pharo, but in case of Pharo we have two challenges, and these are also challenges that are similar for other dynamically typed languages. So first, in Pharo there are no public-private keywords, so no keywords that define method visibility, and this means that every method in Pharo is considered public, but of course in reality not every method is supposed to be used. So there are many methods that are not meant for clients as an API, but it is not easy for us to know which methods are those. So as far as we are concerned, everything is public. And this introduces false positives. Second challenge also introduces false positives because as a dynamically typed language, in Pharo it is not clear when we have a method call, it is only a method name. It is not clear from which class will this method be called, and it is only during execution that this will become clear. So also we don't know what are the argument types, we don't know what are the return types, and like this it introduces a lot of false positives to our data set because we only have the method names, and sometimes we think it is the good replacement, but in fact it is not. So these are two challenges that we will have to deal with. Now I will present to you the approach that we propose. So we call this approach DepMiner. So it's an approach for mining frequent method call replacements from the commit history. So first what we do, we collect the data, we take the commit history, and for every commit we calculate the diff to the previous commit. So the diffs that are provided by version control systems such as GitHub, such as Git, for example, those are the line-based diffs. And for what we want to do, for us it's much more useful to have some higher level representation. So we use the tools provided by Pharo, the tool called Iceberg, but there are also many alternative tools for other languages that parse the source code in the commit diffs, and they provide a more representative tree of removed methods, added classes, removed classes, and method modifications. And for example, we can access the old and new source code. Then by parsing this source code, we can also we can infer what are the removed method calls and added method calls that were what was done by every commit. Okay, so now we also introduced the concept of a method change. So what is that? It's basically one method that was modified by one commit. That's it. So here you can see the example of method change. That is one method, and in one commit, those are the red lines that were removed and green lines that were added. So as we said before, we represent it on a more high level. So in fact, we can represent every method change as a transaction, which is a set of removed and added method calls. And in fact, for our study, we will be only interested in those sets. So basically, our whole data set of commits will be simply the sequence of sets where each set contains removed and added method calls. Okay, so now second step of our approach, we need to detect breaking changes, and there are many different kinds of breaking changes, but in this study we only consider one type, which are the missing methods. So those are the methods of the old API that do no longer exist in the new version of the library. So here comes the first challenge, because as we mentioned before, in Pharo there is no method visibility, which means that we don't really know what is part of API. We don't really know which methods are public. So to address this challenge, we define certain heuristics for Pharo. So we know that, for example, test methods, they should always be considered private, the same as example methods, baseline methods, help methods, and so on, and also methods that are that have certain protocols. So these are kind of tags in Pharo that where developers can directly mark that, okay, this method shouldn't be used. So we write this kind of heuristics, and they can also be written for other languages. And for Pharo, we publish them in the public repository. So this way we can kind of, we cannot clearly know what is an API, but we can infer, we can use our knowledge of the language to infer that at least this is this is our approximation of what API is in this project. Okay, so on the third step, we use the market basket analysis to find the frequent method call replacements. So here is the small example of classical market basket analysis on supermarket. So what happens is that we have 5 clients, You can see them on the left, and five customers, sorry. And each customer buys certain products in the supermarket, and those are the database of transactions. And what we want to do, we want to know what are the products, what are the groups of products that are frequently purchased together. And also we want to know for customers who buy bread, what are the products that we can recommend to buy together as bread. So how it is done is that we see that we calculate all possible combinations of products, and we can see that bread and butter, there 60% of customers who buy bread and butter, 60% of customers, they buy bread and butter together. So this means that this set of items have high support. And also milk and cereal. We see that out of 5 customers, 3, so 60%, they buy milk and cereal together. Now, for the second question, we also see that for customers who buy bread, there are 4 customers. So customer 1 to 4, they all buy bread. And the first 3, they also buy butter, which means that we have a 75% confidence that if a customer buys bread, they will also probably want to buy butter. Now, similarly, we can apply this technique to method calls. So as I mentioned before, we can represent method calls. We can represent a method change as a set of method call added or remove method calls. So like this, we can ask a question: what are the operations? What are the method call additions or removals that are commonly appear together? And second question, which actually the one that we want to know, is what are the method calls that are added when a given method call is removed. So for example, if next is removed, what are the method call that is commonly added? So now when we get these associations, we can do this using the data mining algorithm such as a priori. We have now the missing method, know which method we're looking for. We have the association rule that can tell us about this method, and from that it is straightforward to generate the deprecation. So here you can see that we can recommend to the library developer, if a method was missing, we can recommend to reintroduce this method with the deprecation. And deprecation will have a deprecation message and the transformation rule. Now here comes the second challenge, because in fact because Pharo is dynamically typed language, and this will be the same in other programming languages that are dynamically typed, we do not really know from which we know that this method call was replaced with that method call, but we don't know from which classes they come. And it means that, for example, we don't know if node, for example, has a method next node. So it's very hard for us to deal with this challenge. So in fact, it remains a limitation of our approach. But what we do, we simply restrict our approach to only use those association rules that propose antecedent and consequent that are both defined in the same class in the new version of the library. Which means that, for example, if in the new version node does not define a next node method, then we discard this association rule and we don't recommend this to library developers. So here you can see the big picture of the whole approach at a glance. So we have a library with 2 versions, we collect the data, we detect breaking changes. Then for each missing method, we mine frequent method call replacements. We generate a deprecation, propose it to library developer, and if library developer accepts it, they can submit it and as pull request to the new version of the library. Now we evaluated our approach on 5 open source projects. So to do that, we implemented a prototype tool in Pharo for our approach. So here you can see the screenshot of this tool. And we selected 5 open source projects in Pharo system. So you can see the red one is Pharo itself, is the biggest one. So the size here, the size of each circle represents the number of methods in each project. So this red part is just a very huge, massive circle that represents Pharo. And the smallest one you can see there is data frame. It has only 661 methods. Also, the color represents the type of the project. So the green ones are the tools, and blue ones are the libraries. So and red one is the case. So what it means is that library is the project that is supposed to be used by other programmers. So it has the API, and the API is well maintained. So because API is the most important part of this project. Tools are the projects, they're like smartphone apps. So they're supposed to be used by clients but not really by other programmers in general case. And SDK is a special type that we use for Pharo, because Pharo is the big massive system that includes many different libraries in it. So those yellow people, they're the reviewers. So here we can see how many reviewers we used per each project. So generally it's one, except for Pharo, because Pharo is big, so we used 4 different reviewers for Pharo. Here you can see the results of our experiment. So each bold, the number represents the number of recommendations for each project, and the green parts, the green segments, those are the accepted recommendation. So the light green are the non-rewriting deprecations, and the dark green are rewriting deprecations, so with transformation rules. And as you can see, for the top parts, so for Pharo, Famix, and data frame, a good number of deprecations was accepted. So for Pharo and Famix, those are more than 50%, and for data frame, those are 4 out of 11. But so considering this data frame is a really small project, it's a good result. But for Moose and Pillar, there is almost nothing. So this is a very interesting result. Why? Especially because Pillar, for example, is pretty big. So you can see that Pillar is almost as big as Famix, and for Famix we get a lot of recommendations, 87. Well, for Pillar we get only 1. So we can speculate, we can try to explain this by that Pillar and Moose are both tools, they're not libraries, which means that they don't have really important API, and maybe between different versions this API does not change so much. So you can see that our approach is probably more suitable for libraries or SDKs such as Famix, DataFrame, or Pharo. Finally, those are the limitations of our approach, and they imply also the directions of the future work. So first, this approach is not very useful for methods that are not used by the library or not tested, because what we do, we learn from the self-usage of library, so how library uses its own API. So if the method is not used or not covered by tests, we cannot learn anything about this method. Second, we depend on the unordered set of method calls, which means that we completely lose all the information about the order of these method calls, which is also a limitation. Third, we search in the entire commit history, and this could be maybe beneficial in future work to try searching more locally. So to identify a place where a certain method was removed, and then only in the commits that are after this removal, we search for the effect of this removal. So what were the changes done to the code when this method was removed? Because now we look in the entire commit history. And finally, reflective operations. So modern programming languages like Pharo, they allow a lot of reflectivity, which means that sometimes methods can be called by their name. So we give a string and we say, okay, call a method that has a name like this. And those kind of calls we cannot detect. So we only detect the normal method calls that can be represented in the abstract syntax tree. So to sum up, in this work, we propose an approach to help library developers by generating deprecations that have transformation rules, and those transformations can be used to automatically update the client systems. So our approach is based on frequent method calls analysis. So it finds frequent method call replacements in the commit history. We implemented this approach in the prototype tool for Pharo and applied it to 5 open source projects, and 134 deprecations that were generated by our tool were accepted into these projects as pull requests. So thank you very much for your attention. Bye bye.